Good morning, everyone. Today we'll wrap up chapter 5 by going through example 5. We have looked at examples, 4 examples so far. Examples 1 and 2 dealt with the sources, meaning the voltage and current sources. Now we can combine those. And then examples 3 and 4, we looked at components, inductors and capacitors specifically, to see how we can derive voltage and currents by applying Ohm's law. Now we'll combine everything together. In example 5. Okay. So in the interests of working through the class efficiently, I have already made the annotations in the slide so that students can concentrate simply on taking notes. Okay. So I will go over the step-by-step detailed solution right here, but you should already have access to these annotations, the entire solution. Okay, so example 5. We look at it and we see it's comprised of 3 components, R, L, and C. We can also call this as a RLC circuit. So again, RLC circuit with a voltage source Vs. RLC circuit with a voltage source Vs. Okay. And some other things that are given to us are the component values. The current direction is also marked in there. The first thing I always tell students to do for AC analysis or AC circuit is to draw out the equivalent impedance diagram. Okay. So you draw out the equivalent impedance diagram, meaning you replace every single component with its equivalent impedance. And that circuit is drawn right here. Okay, the equivalent impedance diagram. So if you look at this diagram in isolation, meaning we didn't know anything about this diagram, no values, no quantities, anything was given, what do we see? We simply see 3 resistors. They are connected in series and a voltage is being applied, right? So I always tell students to do this because it lowers the stress levels. When we talk about chapter 5, AC sinusoidal state analysis, students encounter differential equations for inductors and capacitors. Always tell, draw out as a first step the equivalent impedance diagram, and then you think back to chapters 1 and 2. Okay, there's nothing new in this analysis for this chapter. The analysis techniques are exactly the same. There's no difference whatsoever. The only thing that is different is the math. Okay. So what do we see when we look at that impedance diagram? We see 3 resistors in series, or in this case, 3 impedances in series. Impedances add up the same way as resistors. So that determines your best approach. Chapter 2, we first looked at combining resistors in series, then combining resistors in parallel, and then we looked at techniques where you combine a large resistive network, you reduce it down to one single equivalent resistance. And that's the same approach we take for any AC circuit. Again, remember, when I say AC circuit, the thing that makes it AC is the application of an AC source. The components are the same. Resistors, inductors, capacitors. It's just that their behavior changes because the source is now AC. So AC circuit is AC source, it's still RLC. And your analysis techniques are also exactly the same. So series impedances, you remove Vs from your analysis and you determine the total equivalent impedance as seen by the voltage source. When you hear the words as seen by, you remove it from your analysis. You analyze the rest of the circuit between those open terminals. you need to find the value for one single equivalent impedance as seen by the voltage source Vs. We are using the technique called series parallel equivalent analysis. I think homework number 7. Chapter 2, first technique that we saw, right? And that is what we're doing here. Finding ZEQ. And ZEQ depends on the circuit combination, depends on how the components are connected. Here it's connected in series, and so ZEQ is R plus ZL plus ZC. As straightforward as that. Let's take a pause. I want to make sure everyone sees that. Let me know if you have any questions. Any questions? Again, this circuit has a series combination of R and C. So our approach is to combine all of them together in series. If it's in parallel, again, you can combine them, but you use the parallel equation, the reciprocals. If it's series parallel or parallel series, then you would combine it accordingly. If you have more than one source in there, you would use mesh current analysis or node voltage analysis, except it's not complex number math. You can relax. 201, I don't ask you to do mesh current or node voltage for AC analysis. Okay, so if we need ZEQ, we need the values for the individual impedances. So the individual impedances, we go to our source because the impedance response of an inductor and capacitor depends on the source frequency. And again, important reminder, the resistor, inductor, and capacitor components, they affect the magnitude, the Y direction. They affect the voltage, they affect the current. Resistors do not affect phase. Inductors and capacitors affect the phase. And none of those three affect the frequency. The frequency does not change. The frequency always remains the same. That is not affected at all. We take our source and we compare it to the standard expression. V of t is Vm cos omega t plus theta. And from there, we obtain the values for the three quantities, Vm, omega, and theta. 100 volts, 500 radians per second, and 30 degrees. If your source is not in cosine, if it's in sine, you convert sine to cosine. Remember, you want to write the phasor, you want to perform a phasor transform, you convert the sine to cosine. So always make sure you do that. Once you have the value for omega, you can directly write down the phasor for the source. In this case, it's in cosine, magnitude 100, phase angle 30, 100 with an angle of 30. Phasor is done. And then we take the standard equations for ZL and ZC, plug in the values for omega and the component values, and find ZL and ZC. And I will explain what I have done here. I don't have a programmable calculator. You've heard me say this multiple times, right? Also, engineers, as engineers in training, you should be aware of how we are working through these equations. So I know in advance, I need to find ZEQ. ZEQ means I'm summing up, or I might have a reciprocal in there if it's parallel. Then I need to perform a division. Then after that, once I have ZEQ, I'm going to apply Ohm's law, meaning I need to perform multiplication and division. So some equations, I would need the polar coordinates. Other equations, I would need rectangular coordinates. So my approach always has been, and I developed this habit over years, my approach has always been to find the quantities in both polar coordinates as well as rectangular coordinates. So when I find ZL and ZC values in a circuit, I always tend to find both the value of ZL in polar coordinates and the value of ZL in rectangular coordinates. And that is what I've done here. I've used the equation. The first is in polar coordinates. The second is in rectangular. Exactly the same equation, just two different coordinate systems. For an inductor, voltage is always ahead of the current. Eli the Iceman, page number 15. So equation in polar coordinates is omega times L with an angle of plus 90 degrees. Right? Z is impedance, ZL is VL divided by IL. Magnitude of voltage divided by magnitude of current. Phase angle of voltage minus the phase angle of current. Voltage is always ahead of the current by 90 degrees. So impedance ZL is always plus 90. That does not change. That's the standard equation for impedance of an inductor. In rectangular coordinates, ZL is simply J omega L or J 2 pi FL. J omega L, omega is 2 pi F. So you find the values, 150 with the angle of 90 degrees or J 150 ohms. Yes. No, you just, the question being asked is what if you had a current source in there? So you would just proceed exactly the way it is. When you say flip, are you talking about the equation? No. No. So if it's a current source, it doesn't have anything to do with the inductor itself. The inductor by itself has a impedance angle of plus 90. Whether you apply a voltage or a current does not matter. Okay, and ZC is 1 over omega C with the angle of minus 90 because the voltage is behind the current by 90 degrees. So theta V minus theta I for a capacitor is always minus 90 degrees. That's the standard expression. In terms of rectangular coordinates, it is 1 over J omega C, reciprocal of J omega C. And 1 over J, did I do this last time? 1 over J can be represented as 1 over J. Multiply and divide by J. This gives you J over J square. J square, of course, is minus 1. So reciprocal of the imaginary number is the negative imaginary number. 1 over I is minus I. That's where it comes from. So capacitor impedance, ZC, 1 over J omega C is minus J over omega C. In the polar coordinate system, it's 1 over omega C with an angle of minus 90. All adds up. All right, let's take a pause. Let me think over all of that. Let me know if you have any questions. Because this determining ZL and ZC for any given circuit is standard. What happens after this depends on how the circuit is configured or how it's connected. But ZL and ZC you would have to determine for any circuit. Yes. Not always. It's just easier. And again, as I said, if you have a programmable calculator, those programmable calculators can take any coordinate system and perform any arithmetic function. You could multiply two rectangular coordinate numbers together. You could divide two rectangular coordinate numbers together. You know, a calculator would be able to do that, depending on the make and model, of course. It's just easier to do it that way. All right, any questions? Any other questions? Is everyone good so far? Finding the individual impedances, right? Now, from this point on, you actually apply your circuit analysis technique. ZEQ in this case, of course, is simply the sum of all three components. So R plus ZL plus ZC. And I went ahead And that here, ZEQ is 100 plus J 100 ohms. And at the same time, I know my next step is going to require a division, Ohm's law. And so I went ahead and also found ZEQ in polar coordinates. When the rectangular coordinates, meaning the real portion and the imaginary portion of a vector is exactly the same, the resulting angle will always be 45. Always. 100 plus J 100, meaning this real axis is 100, imaginary axis is also 100. If you add them up and you form a right angle triangle, it's an isosceles right angle triangle. One angle is 90, the other two are 45. Exactly bifurcates in the middle. Okay, so the resulting vector will always have an angle of 45. Could be minus 45 depending on which direction it's pointing, but the value will always be 45. Okay, so now I have ZEQ. My circuit looks like this at this point. I have voltage source Vs applied to ZEQ and current I flowing through it. One single current that's flowing through all four components, the voltage source and R and L and C, right? The current is the same for all four components. Vs supplies I to all components. So you apply Ohm's law and you find the value of that current I. That's it. V equals IZ. So I equals V over Z. V is voltage source Vs. Perform the calculation and you obtain a value, a phasor representation of that current, 0.707 with an angle of minus 15. You write the answer in the time domain, I of t, because that is what is asked of us. I typically, when I was a student, even if it was never asked, I would always write the final answer as a function of time. Just to be safe. Okay, so I of t, magnitude 0.707, phase angle minus 15. Frequency is not affected. So when you perform the inverse phasor transform or the reverse phasor transform, you're going from the frequency domain back to the time domain. Your frequency is the same as the source frequency, 500. That does not change. Okay, that does not change. So function, time domain function of the current, magnitude 0.707, cos of 500t, phase angle minus 15. That's how we write the inverse phasor transform. Okay, makes sense to everyone? Okay. All right, then we found the resulting current I. That same current I is flowing through all four components. Now, if we wish to find the inductor voltage or the capacitor voltage, you can perform differentiation. Chapter 3, VL is L di over dt. You can differentiate this current and find the voltage that way, or you integrate this current and find the capacitor voltage. But thankfully, we don't have to do it. We can apply simple Ohm's law again because complex numbers. Hence, as I'm fond of saying, hence, we are using complex numbers to make the math less complex. So VR is simply given by I times R, VL is I times ZL, and VC is I times ZC. You apply Ohm's law first, find the total current I, then you apply Ohm's law second time, find the three voltages, and that's it. All right, let's take a pause while you write it down, think over it. Let me know if you have any questions. Okay. Yeah. So the question being asked is, if there is no imaginary value given for a AC source, should we assume it to be zero? The answer is yes. If nothing is stated, you always assume it's zero. All of engineering in general, all of scientific principles also, you always make certain assumptions. If something is present, you make an assumption. If something's not present, you make an assumption. So that's a very good question, a very good point. Without assumptions, we would never be able to solve anything. Yes. Yes. The resulting current will always have the same frequency. That does not change. The components do not affect frequency at all. They only affect the amplitude and the phase. Yes. No, it's fine. Ask. Mm-hmm. So you're talking about going back to like chapter 3 or 4. So let me understand your question correctly. So you charged up the capacitor to a certain voltage or current, then we removed it from the source, and now you're discharging the capacitor, and you're asking whether the frequency remains the same. The answer is yes. Doesn't change. Yes. So when we say, so the question being asked is there a frequency at steady state? So let's back up to the beginning of chapter 5. I probably just mentioned it once, but what we're analyzing in chapter 5 is the steady state AC response. When you apply DC or when you apply AC, there is a transient period. There is a transient period where the response, meaning the voltage of the current in an inductor capacitor, is fleeting, hence its transient response. It's the same for DC. It's also the same for AC. So AC will have two responses. It'll have a transient response, and it'll also have a steady state response. The steady state, so the confusion arises from the fact that AC itself, the voltage or current is always fluctuating, right? It does not stay steady with time. And then transient also, we say the same condition, meaning it's not steady with respect to time. So there's a conflict with those two. Am I understanding your question correctly? Right? So it's two separate things. So there's a transient response where the transient response decays to zero after some point in time. And then what is left is just a steady state response. Now, the steady state response is also a function of time. So in that case, it might look something like this. You'd have a voltage, something like this. You'd have two different responses. So if we analyze just the transient response, we'd be able to see that separately. And we'd analyze the steady state response, we'd be able to see that separately. The entire chapter, we're only looking at steady state sinusoidal responses. So this entire analysis is just limited to steady state responses. Hence the steady state sinusoidal analysis. We are not looking at transient response of AC circuits. We keep that for EE major classes. If you want to take that as a tech elective or something. But good question. I like discussion. I wish we had more. When we get to semesters, we'll have more time for like discussion and stuff. Okay. Any other questions? Does the approach make sense? Again, as I said, this is a simple, straightforward circuit. When it goes to multiple sources, node voltage, mesh current analysis, then your approach changes in your multiple sources. We don't do that for 201. It's either series parallel or just series or just parallel. That's all I keep it to. Okay, we don't go more than one source in AC analysis. Okay, all right. Other approach is to skip Ohm's law and just apply voltage division. Series connection of resistors, voltage is applied, fraction of the supply voltage appears across each resistor. Same concept. You apply voltage source to a series connection of impedances, a fraction of that voltage source appears across each impedance. You can directly apply voltage division. You have the answers, you have the equations. Practice outside of class. See if you can find or if you obtain the exact same answers. You should. There's no reason why you shouldn't. Okay. So students, several students have requested of me, they would like to practice more. So I have, and this has been a few weeks, so I apologize. I'm going to add a few more extra problems in the homework, so you can go back and practice more if you want. But I would also state, as we have gone along in this class, every time I've stated that there are multiple approaches to the exact same problem, meaning we did one example each for node voltage, for mesh current, and for superposition. You can apply you can apply all three techniques to all three circuits. I'm bumbling and fumbling my way today. I don't know why. Again, we did one example each for each technique. So you can apply all three techniques to all three circuits. That's a good way to practice because you know the answers, you know the approaches. You can change your approach by changing the reference node. You can change the direction of the mesh current, and you can solve the exact same circuit with different approaches. And that is good practice. Okay, that will be good practice. You have the circuits from the quiz. It's the same circuit. You can take multiple approaches to solve for that same circuit. That would be good practice. Okay. So again, practice. You have the equations. I have provided the equations for the voltage division. You have the final answers. Go ahead and practice, and that would hold you in good stead. Phasor diagrams, as I stated last class, all you need to plot a phasor diagram is the angle and the length, and these are plotted not to scale. You can simply take the angle, plot a line at the angle, and that's it. Mark and note it, and done. So voltage source Vs had an angle of plus 30. So you draw a line or an arrow at 30 degrees, note it as Vs, and that's it, done. You don't have to, you can note the magnitude. I try to keep it clean. Otherwise, it was getting very cluttered in there. Okay. Note the angle of the current. Minus 15. Minus 15. So, minus 15. The voltage had plus 30. The resulting current is minus 15. The point I'm making is the voltage or currents that appear in a circuit will have random magnitudes, will have random angles. It all depends on the values of the components, and it depends on how they are connected in the circuit. Okay, so it's a series connection. Voltage for the source is applied with with an angle of plus 30, but the resulting current is minus 15. So again, the answers could be anything. If you obtain an answer while trying to solve a problem in a quiz or an exam, it doesn't mean that your answer is incorrect. Right there. Plus 30 and minus 15. Okay. The current is the same for all four components. Voltage source Vs plus 30, but the current is phase shifted by 45 degrees. Resistor voltage, VR, also has an angle of -15. A resistor does not affect the phase of its voltage and current. So if the current for a voltage is -15, then the resistor voltage, the voltage for that exact same resistor, also has an angle of -15, which is what we obtained. And that's how we plotted two arrows on the same line, two vectors on the same line. VR and IR have the same phase angle, -15. Obviously, this is not to scale because I has a magnitude of 0.707. Vs is 100 volts. It's more than 100 times long or longer than I. Okay. So only the angle matters. The length does not matter. So plus 30, -15, I and VR are in phase. That leaves us VL and VC. VL is plus 75. Voltage for an inductor is ahead of its current by plus 90, by 90 degrees, which is what we see here. Okay, which is what we see here. The current I is also the current for the power supply. It is also IR. It is also IL. It is also IC. That current I is the same for all four components. All other voltages are measured with respect to that same current. Inductor voltage is 90 degrees ahead of that current, plus 75. Plus 75 and -15 is a right angle of 90 degrees. Capacitor voltage VC is 90 degrees behind that same current, -105. -105 and -15 are exactly 90 degrees apart. Let's take a pause while you note that down. Does that make sense, everyone? Okay. The reason that the inductor voltage and the capacitor voltage are exactly 180 degrees apart is specific to this case, is because they share the same current. If they did not share the same current, it could be any degrees apart. They might even have the same phase, who knows? It depends on how the circuit is connected. It depends on how it's configured, okay? If they share the exact same current, then yes, it will always be 180 degrees apart because inductor voltage is plus 90, capacitor voltage would be minus 90. But if they don't share the same current, then it could be any other random value. That's the two other important points. Okay, questions? Does it all make sense? No more questions? Okay, then I want to talk about something on here. And I pointed this out earlier. This pertains to lab number 6. Inductor, an ideal inductor, does not have any resistance. Okay. However, in real life, a current carrying conductor, current carrying wire inherently has resistance, it has inductance, it has capacitance. The values of these quantities do not rise to the level of interference, so we don't care about those. But it has inductance, it has resistance, it has capacitance. An inductor is simply made out of a conducting coil of wire. You take a conducting piece of wire and you wind it up in a spiral coil. That coil can be very tightly wound. So the length of that coil or the length of that wire when stretched out will be very, very long. Even a tiny inductor this size would be very long in terms of length. If you remember chapter 3, inductor L is directly proportional to the number of turns in the wire. Remember, the higher the number of turns, the higher the value of the inductance. However, that has a drawback. Resistance L is given by rho L over A. Rho is resistivity, it's a material property. L is the length of the wire, meaning depending on how long the wire is, and A is the cross-sectional area. So if you have an inductor that has a large number of turns, like 1,000 turns, if you unwind that coil and you stretch it out, it's going to be a very thin wire running for like tens of meters, maybe even hundreds of meters, perhaps, right? Very long. As you see the equation for resistance, it is directly proportional to the length and is inversely proportional to the area. Area is the cross-sectional area of that wire. So the longer the wire, the higher the resistance. The thinner the wire, the higher the resistance. So if you're making an inductor out of a very thin, long piece of wire, it'll have resistance in real life. Make sense? That resistance is part of that inductor. I just stated, right? It's a piece of wire. If you take this inductor and you measure the inductance L between A and B, you will get a value for L. If you measure the resistance between A and B, you will obtain a resistance between A and B. And that resistance is noted as the inductor resistance RL. Inductor resistance RL. Okay. It's physically the same component. You cannot separate it out. Physically, it's the exact same component. Make sense? You cannot separate it out. Electrically, we represent it as an inductor in series with that resistance between A and B. This would be L. This would be RL. And this is what you're doing in this week's lab. So the labs were written with the assumption that we're using high quality inductors. There is a measure that we describe the quality of an inductor, which is Q. Can be used for capacitor also. But QL is the ratio of the reactance to the resistance RL. Ratio of the reactance to the resistance RL. Ideal inductors, RL is 0, quality is infinite. Real life, RL is around 4 or 5 ohms, typically less than 5 ohms. So the labs are written with high quality inductors. We did not have low quality inductors at the time. So what you do in those labs, the lab write-up states, you add an external resistor in series with your high quality inductor to simulate or model a bad quality inductor. You guys with me? You're using an external resistor to simulate a bad quality inductor. But since then, we have acquired low quality inductors. I prefer using those low quality inductors. I don't like using the high quality ones. So it depends on who is teaching your lab and what their preference is. Okay. So if you're taking the lab with an instructor who might be using either high or low quality inductors, but asks you to add an external RL, then you would have, if you have a low quality inductor, you'd have 2 resistors in series with your inductance. Make sense? Right? In my labs, I don't like to do that. I prefer to use the low quality ones. And again, this is something I go in the lab also. But again, this is something that even if you're not taking the lab, is something that you should be aware of. Q for an inductor describes the ratio of its reactance to its resistance. It's a dimensionless quantity, no units, because units for reactance is ohms, units for resistance is also ohms. And what you're doing in today's lab, not today, in this week's lab, is verifying KVL. Verifying KVL using graphical methods. Okay, you're verifying KVL using graphical methods. Okay. There are no more questions. We can go Well, now we can go. Any questions? Any questions at all? Yeah. Good question. I would say yes. So the question being asked is, would we be asked to well, I would say always say retain everything we studied in class, but it's not always possible. So the question being asked is, would we be assessed this topic on a quiz or in the exam? I would have to say no at this point. I would say no. Okay. So if there are no other questions, we can say that we are at an end of chapter 5. We'll introduce chapter 6 briefly, but I won't have time to do the example problem. The homework that's due for chapter 6, the first one, is straightforward. So until I cover the example, so I will cover the example on Friday. So the homework will not be due until after Friday. Okay. And the homework problem, it's only 1 or 2 problems in there. It's exactly the same as the example that I will solve in class. So it shouldn't take you long to knock it out. But as I said, in any case, we are not going to do that until after Friday. So chapter 6 is frequency response. And we'll have to adjust our thinking a little bit for this chapter. Okay, and I'll explain what I mean. So here are listed some of the frequencies, the most common electrical signals that we use in everyday life. Okay, whether it's a wired connection or whether it's a wireless connection, all signals are transmitted using certain frequencies. Okay, when I say signals, it's a generic term, it's an umbrella term that encompasses voltages and currents. Okay, signals just means it's a quantity that's traveling from one point to another point. So by this time, I think everybody should be able to answer. What is the frequency of the power outlet? 60 hertz. Outside of North America, it's 50. Most places. There might be 120 some places. 120 is also used in, now 120 volts is used, but 120 hertz, there are some applications where we have used 120 hertz. Okay. As I was saying, North America, 60 hertz. Outside of North America, it's 50 hertz. Very low frequency. Normal human hearing range, 20 hertz to 20 kilohertz. Most people like me, between 100 hertz to like 14, 15 kilohertz. Again, not very high compared to what we use in everyday life. AM radio stations, FM radio stations, call signs of the radio stations are the broadcasting frequencies. 680 AM is 680 kilohertz, 101.7 FM is 101.7 megahertz. That's the frequency it's sending its frequency out. Okay. Anytime you tune to a radio station, you are setting the reception frequency for your radio to match the transmission frequency for that radio station. Cordless phones, which nobody uses anymore, obviously. Cordless phones, wireless routers, microwaves, they run and operate at frequencies of 2.4 gigahertz. The wireless router bands are the transmitting frequencies, 2.4 gigahertz and 5 gigahertz, dual band routers. FCC, Federal Communications Committee, controls the frequency spectrum in the United States. Every country's government controls the airwaves. They control the land, they control the sea, they control the air, right? FCC controls the frequency waves. Frequency is valuable. It's referred to as precious frequency spectrum because it's limited. Across the world, most frequencies are set, meaning AM in one country is the same as AM in another country. It's not going to be a different band of frequencies. Different radio stations in every country will have different frequency bands, but it's fixed. Television is broadcast at a certain frequency band. Cell phones are broadcast at a particular frequency band. My phone is an international model, so it can work with a variety of carriers all across the world. How it does that is what we're going, well, not how it does that, but Why can it only work with certain carriers and why not with others is what we're going to study in this chapter. Okay. So 3 major wireless carriers in the United States: AT&T, Verizon, and T-Mobile. There was Sprint. Sprint was taken over by T-Mobile. So the physical infrastructure is now only 3 companies. Every few years, these companies will bid on FCC auctions. And FCC auctions off the right to use certain frequencies for a certain period of time. Some frequencies can penetrate farther through walls. And hence, when we say, oh, you had Verizon network or you had AT&T, I had poor reception here, I had good reception here. Well, it also depends on how the construction is done. There's a lot of concrete, there's a lot of rebar structures, like metal structures inside the walls. It's going to short out your electrical signals. It can't come through. So that's one of the reasons. One of the other reasons is lower frequencies can travel farther than higher frequencies. So AM can travel farther than FM. Same thing with mobile signals. Anyway, so you have AT&T, T-Mobile, and Verizon. These are the only 3 companies in the 48 states that have physical infrastructure. No other company has that. All other companies are simply buying the services from T-Mobile or AT&T or Verizon. That's it. Okay. And all of these companies operate at different frequencies. When they bid on these frequencies, what they're doing is think of them as like roads or highways. Each company is bidding and buying from the government to right to use each highway on a private basis. And only their vehicles are allowed to go through those highways. No one else. So they're physically prevented from using those highways. So electronically speaking, a Verizon phone can work on AT&T and vice versa, but they always say that we are blocked from using it. The reason they block it is, of course, money, obviously, but how they block it is what we're going to study in this chapter. It happens through the magic of filters. It's not magic, nothing magical about it, obviously, technically speaking. And filters, electronic filters, as the name suggests, filter out unwanted signals and only allow certain signals to pass through. Meaning if you have an AT&T phone, it will only work on AT&T because there is a filter at the front end of that phone. It will block out all signals except for AT&T signals that are allowed to go through. As I said, when you set your radio to match the frequency of a FM station or an AM station, you're filtering out all other stations. You're only allowing that particular frequency to go into that radio device. That happens through filters, electronic filters. So the response of that circuit depends on the frequency of the incoming signal. So here's where the where's the adjustment in thinking comes into the picture. So far, we have looked at circuits in terms of voltages and currents. And of course, we'll continue to do that. But now we're going to think of circuits as sealed boxes. That sealed box, network is another name for circuit. Okay. So inside the sealed box, we don't know what's inside the box. We don't care what it does. We only know. So we don't care how it does it. We only want to know what it does. And that is described by its transfer function. We are going to think in terms of combining the 2 input terminals as a pair of terminals. And it's labeled as a port, P-O-R-T, port. On the left side, typically it's represented from the left side. We say it's being input into the circuit. So we have an input port, and we take the output across a resistor or a capacitor or an inductor, and we tie those terminals together, and we say it's an output port. So we think in terms of input port and output port, where we're taking the output. And the quantity that describes it, I discovered it, and so I named it after me, H of F. Not really. I don't know why they chose H. But it's a function of the frequency. And it simply describes H of F is simply the ratio of V out to V in. It simply describes how the input is being transferred to the output by that circuit. If it's a filter circuit, it's going to block some of the input, it's going to allow some of the output to come out. So it's the transfer function for that filter will describe how the input is transferred to the output. That's it. If you note, V out and V in are both phasors, complex numbers. So H of F is also a complex quantity. It is dimensionless, does not have any units because it's a ratio of voltages. We will end class here today and we'll pick up here again on Friday where I will do the example. In the meantime, review. Let me know if you have any questions. Stop by my office. I'll be in my office later this afternoon. And otherwise, I will see you all on Friday.